Hi everyone, this video is covering the topic of the velocity vector. In prior lectures, we've discussed vectors as quantities that have both a magnitude and a direction. One vector quantity that is of particular significance to fluid mechanics is the velocity vector. So this video is going to explain some common notation related to the velocity vector that we will be using throughout our study of fluid mechanics. So the velocity vector is the change in the displacement vector over time. So I can define my velocity vector as a function of my displacement vector d and time t. So this displacement vector itself, this is a change in spatial position with respect to time. And so I can define my displacement vector as a function of time like this. And so because the position can change in up to 3 different spatial dimensions at the same time, this displacement is defined with the unit vectors ij and k. Which of course each have a magnitude of 1 and are respectively in the x, y, and z direction. And then here, the x, y, and z these are the magnitudes of position in the ij and k directions, respectively. So as we said at the start of the video, the velocity vector is defined as the change of this displacement vector over time. So in order to derive our velocity vector, I can take the first derivative of my displacement vector with respect to time. So my velocity vector, function of displacement and time, is going to be equal to the first derivative with respect to time of my displacement vector, which itself is a function of time. Right, so I've just got each component of my displacement vector, x, y, and z, and I've taken the first derivative of each of those components with respect to time, yielding dx dt, dy dt, and dz dt, and then each one is multiplied by our unit position, or our unit vector, ij and k. And so each one of these derivatives with respect to time is going to tell me about a component of my velocity vector. So dx dt, this is another way of writing my x component of velocity. And dy dt, this is another way of writing my y component of velocity, dz dt. Here's my vertical component of velocity. Okay, so if I have a coordinate axis system in my three spatial dimensions, x, y, and z, I can then draw my x component of velocity that looks something like this, v sub x, and then my component in the alternative horizontal axis on y would look something like this. Here's my v sub y. And then in the vertical, I would have my z component. So instead of looking at this in three different directions on an axis, I'm going to just put these axes into like a real-world context that we might use to analyze the velocity vector. So let's say that I have a river channel, right? So here is my left bank. Here's my right bank. Here's my river bottom. And let's say that I've got some water in my river channel. And so here's my free surface. And just to make it look a little bit more realistic about what you would find if you find a river channel in real life, maybe I've got some emergent aquatic vegetation close to the banks. Down here, submerged along the bottom. Maybe I've got some submerged aquatic vegetation. Maybe I've got like some aquatic organisms that are living in my river. And the flow of my river is going to be going downstream, right? So if into the page is upstream in the river, out of the page is downstream, my primary flow dimension is going to be like this one. And by convention, in fluid mechanics, if we have three different components of the velocity vector and one of them is bigger than the others, that one is automatically defined as our x direction. It gets the I component of the vector. And so we've called this so far the v sub x component of velocity. Well, in people who do fluid mechanics every day, all of their careers, maybe they get tired of writing v sub x and v sub y and v sub z, and so we give it a particular notation. And this particular component, the biggest component of the velocity vector, we call it variable u. It's the u component of velocity. So instead of having a v sub x, we just call this u. We also have a name for it, which is the streamwise. It is the streamwise component of our velocity vector, and that's why I've drawn you my little river channel here so you can see where not only the notation of u comes from, but also the name of u as the streamwise component of the velocity vector because it's in the direction that a stream would be flowing from uphill to downhill. So you always think about rivers, water going in a main current from uphill to downhill, but actually if you go to measure velocity in a channel like the one that I've drawn here, the flow is three-dimensional. The other two components, the other horizontal component and the vertical, tend to be a little bit smaller than the streamwise component. So let's start with the alternative horizontal component. So that is going to be going in this direction. So instead of going from upstream to downstream, it's kind of going from the center of the channel towards the right bank, or from the left bank to the right bank. So it's going in that alternative horizontal direction that we have defined on our coordinate axes as the y component of velocity, v sub y. Just like the streamwise component, we have a name for this. We have a variable name, which is little v. Don't confuse this with a big V. This is a little v. So our y component of velocity, little v. And just like the streamwise, we also have a name for little v, and that is the cross stream. So v sub y, little v, we call the cross stream velocity component because it is orthogonal to the stream flow. It's going across the stream. Our final component is in the z, and tends to be small relative to both the streamwise and the cross stream components. So this would be our v sub z, our vertical component, and we give this the variable w. So v sub z. Instead of writing v sub z, we will write little w. And this is also known as the vertical component of the velocity vector. So vertical is always aligned typically with our gravitational field on Earth, and then our two alternative coordinate axes, x and y, are usually the two horizontal. One of them, the bigger one, is defined as the streamwise component, and then the second biggest one is usually the cross-stream component. And so if I want to substitute in our u, v, and w into the equation that we derived on the prior slide for the velocity vector, now I can write my velocity vector, which as a reminder is a function of time and the displacement, as u, my streamwise component of velocity, directed in the I direction, my v, little v, component of the cross stream, plus my w component in the vertical, directed in the k. Thank you to the National Science Foundation for supporting this work under grant number 2335802. Great job reaching the end of this video. And please reward yourself with a moment of Zen. I study fluid mechanics because I love water and healthy aquatic ecosystems. Whatever your passion is, I hope it motivates you to continue your study of fluid mechanics. Thank you.